Assalamu alaikum. My name is Humaira Arshad Bhatt. I did my MSc from GC University Lahore, so I'm Arabian. Right after my MSc, I did 1 year diploma from International Mathematics Masters. For Math Volunteers, I am their content curator and event coordinator as well. So, on the behalf of Math Volunteers, I'll be your host today. Today we have our respected guest speaker Diogo Pires, and he'll gonna present a talk on evolutionary games on crafts. For those who are newer, before I introduced my respected guest to you, I encourage you to go and watch the previous videos on this topic. This is actually the third video of this particular topic. So whoever is new today, so I'll encourage you to go and watch the previous videos on our YouTube channel. Diego is a PhD candidate and a Marie Curie Research Fellow at City University, London. His research interests are developing modeling tools for studying behavior emergence, particularly in context of evolutionary game theory, and often incorporating realistic features of complex systems. His main focus is on understanding and informing aspects of social and biological systems relating to collective actions, population structure, and mobility. We are more than happy, thankful, and grateful to have such a brilliant speaker with us today. So, Diego, I think it's time.
It's over to you. Let's start our presentation.
All right, thanks a lot. Thanks also for the invite. I'm trying to, okay, I'm just going to restart. You can see it now, right?
Yes, we can see it.
I had some notice on top. So yeah, thanks a lot for the introduction, for the invite. I'm really happy to be here, and it's very nice of you to be here on a Saturday. I'm not sure wherever in the globe you are right now. At least here is Saturday morning, but even if it's Saturday afternoon, thanks for being here, for being present. I'm going to talk a bit about evolutionary games on graphs. So this is already, I think, the second lecture, let's call it that you are having related to games and to evolutionary games in particular. But basically, this is the main focus of my PhD project. And as you said in the small introduction that I did, I'm currently doing my PhD at City University of London. I've started 2.5 years ago. And yeah, I'm also part of this network, as you said, the Marie Curie network that Vajid is also a part of. I think you've met a few of our colleagues before in other of these lectures. But yeah, basically, I'm going to talk a bit about evolutionary games. And so I'm going to approach game theory, a bit of evolutionary dynamics, and finally, I'm going to introduce a bit of network science and or graph theory into it, just to, yeah, that's going to be the final goal of this presentation. So just to go a bit over the contents that I'm going to cover, I'm going to start by introducing a bit of the motivation for us to work on these models. And these are basically models that we use to understand behavior, and specifically collective behavior. I'm going to introduce evolutionary game theory. So I think you had a lecture by Gosha 1 year ago on a bit of evolutionary game theory and game theory in general, but I'm going to still do a bit of a recap on what are games, what are evolutionary dynamics, when do we consider a strategy to be stable? And finally, I'm going to talk about cooperation and cooperative behavior. And finally, I'm going to introduce evolutionary graphs or evolutionary games on graphs, evolutionary graph theory. There are a lot of variations of these names for it, but essentially, I'm going to introduce networks onto evolutionary game theory and try to provide a bit of motivation for it, talk a bit about the mathematical framework, but let's say, with an intuitive explanation for it, not really on a deep mathematical definitions. I'm going to talk about cooperation in that context, and then I'm going to introduce a bit more of complexity onto it, but just to do a bit of a spice up at the end, introducing scale-free networks or graphs and movement models. But that's more just like a thing to leave in the open. So first of all, why are we interested in using all these models? So basically, when we think about complex systems, and here we can talk about several different types of complex systems. If you think about human societies or animal communities, or even the most simple biological organisms that we can think of, these are complex entity or complex systems that are made out of individual units. So in the case of human societies, we have humans and all of them interact with each other, but together they kind of build a whole social system. If you're talking about animals, they might form also animal communities, but if you go down to their cells, for instance, these are also individual units that together build a whole organism that we can look at only from a macroscopic level and try to understand what happens microscopically. So these are all very complex systems that have these interconnected entities or interconnected individuals, and we are interested in studying what happens at the bigger at a higher level. So when you look at the whole group of these entities, and not exactly just what happens to each one of them individually. So this is like the basis behind complex systems, and essentially trying to understand these systems has an impact in a lot of different fields, a lot of different research fields. So one of them could be evolutionary biology. And here I have an example of 2 cell colonies. I hope you can see the GIF moving, but basically you have 2 cell colonies, and the one on the left is basically a predators, sorry, I said cell, but bacteria colonies. And the one on the left is a predator colony. So basically you can see it spreading spatially. And when it reaches the colony on the right, they kind of form these collective wave patterns that they use to basically predate on the other colonies. So they form those wave patterns as a way to basically eat up the whole of the other colony. So they kind of behave collectively and they organize, but we're still talking about bacteria. While the ones on the left, so if the ones that don't move to the colony on the right, the ones that stay on this left region of the video, they kind of aggregate together, and you can see they kind of form this body that has some holes poked on it, but basically they form this fruiting body. So basically when they face scarcity, when they don't have other bacteria to eat, they kind of aggregate and form like a fruit made out of bacteria. But if they find other bacteria to eat, they kind of also behave collectively, but in order to form these waves and eat other bacteria more effectively. But what we are interested here is like, okay, there is a sort of collective organization of behavior in these bacteria, and this is of interest in evolutionary biology. But if we move to more complex systems, like for instance, let's say communities of meerkat in this case, they also behave collectively in the sense that they build these very complex systems of tunnels where basically they have chambers and rooms. And this is only achieved if they actually cooperate and coordinate their actions in order to build these complex systems. So also, like all of these things that I was talking about, collective behavior and in complex systems is also of interest to ethology, or basically the science of animal behavior. But if we move to humans and we talk about evolutionary anthropology, for instance, it's also interesting to think, okay, how do humans behave and why do they behave like that? Did they evolve to behave in a particular way in the context of their communities? And specifically when we move to modern societies, there are a lot of different fields that branch out here, but essentially in the context of social sciences or in economics, we think about individuals as social or economic agents that have an impact on those around them. So we are interested in understanding not only how these individuals interact with each other, but how macroscopically, when we look from above, how the whole of these like communities or groups or societies or bodies, how do they behave collectively? How are they organized? And this is why basically the main motivation for us to use these modeling tools and to try to understand any emerging patterns from there in terms of what kind of behavior do we see appearing on populations. So, and this is where evolutionary game theory comes into place. So in the context of evolutionary game theory, we look at interactions between these different individuals through the lens of a game. And the game is simply defined by 3 main aspects. One, the players that are interacting, basically what are the individuals that are part of this interaction. 2, what kind of strategies they have available to them. So what are the actions that they have at their disposal? If we're talking about you have to make choice A or B. This is it's a more simplified scenario, or where you only have a binary choice. But if you have, for instance, if the choice you're making or the game you're playing has to do with how much money you want to invest on something, this is a continuum set of choices, right? You can invest €1 or $1, or you can invest 2 or 3 or 4. Basically, you have like a whole range of a larger set of strategies that you can use. So this is the second element, the strategies that you have available, and 3, the payoffs that you get after the interaction. So after everyone has chosen their strategies, what do you get from that interaction? And when you're talking about, for instance, 2 individuals interacting, one with the other, and they have 2 strategies available to them. So this is the simplest case. We can define the game and the payoffs that they receive through a 2 times 2 table. Oops. I think there is something missing. Okay. So, perfect. So basically, let's say we have individuals that are playing one of the strategies. Let's say I can't use my pointer for some reason. So I can't use my mouse. But okay, but you can see you have 2 types of individuals here. Let's say the 2 cartoons that you see here. And when they are playing against, so let's say the transparent one is playing against the black one. So when they are playing one against the other, what do they receive? And this is what is defined when we use a 2 times 2 table. So let's look, for instance, at the donation game. This is a game that, if you heard about the Prisoner's Dilemma, this is very similar to it, or it has a similar basis to it, because the payoffs are ordered in the same way. But essentially, a donation game is a game where, when 2 individuals interact, if one chooses to cooperate, let's call the dark ones the cooperators and the transparent ones the defectors. So when, let's say, one individual interacts with the other, if they cooperate, they will pay a cost C for the other individual to receive a benefit B. Okay. So when 2 cooperators meet, they will receive each a benefit from the other cooperator, but they will each pay a cost C for the interaction. Okay. When a cooperator interacts with a defector, the cooperator will basically pay a cost C, but won't receive anything because it's interacting with the defector. Whereas so they will receive a payoff -C, whereas the defector will receive a payoff B, because they will receive the benefit from the other individual cooperating, but they won't pay a cost. When a defector interacts with the cooperator, it's basically the reverse. So the defector will receive B, but won't pay any costs, and the cooperator will pay C, but won't receive any benefit. And when 2 cooperators interact, none of them pays costs, and none of them will receive benefits, so they both receive 0. Okay, so this is the basis of the game. So do you have any questions so far? I don't know if you want to leave that for the end, but maybe we can do a bit of a checkpoint every now and then. Okay, I'm not sure if there is a chat. I can't open it. So so this defines interaction between them. But what we are interested here, what I was introducing before, were populations of individuals. We are interested in understanding the whole of the complex system, right? Not just how 2 individuals behave when they're facing each other. So that's why we introduce evolutionary dynamics here. So we consider a population of individuals. Let's say here it's a very small population with 3 individuals. They each have their particular strategies, and we consider it to be well mixed initially. This means that they all interact with each other at the same frequency. Okay, so we count the fitness of each individual as being their accumulated payoffs of each interaction. So let's say one will interact with like 2 others, they will receive 1 payoff from each interaction. The fitness will be the sum of those 2 payoffs. So basically the sum of the outcomes of each game that was played with every other individual in the population. And then we consider the evolutionary dynamics to follow a stochastic update rule. So we have a finite population, and the way that it goes is basically you first choose 1 random individual to leave the population. Basically means that this individual will die. And then we choose someone else to basically reproduce. So it will have 1 offspring, and this offspring will replace the individual that was first chosen for death. Okay. And this will be done proportional to the fitness of each one of them, okay? So someone that has a higher fitness will basically have a higher probability of reproducing, of being of basically spreading their behavior in the population, okay? The idea of fitness comes from biology, and it basically reflects how many offspring on average each individual have. But when we move to this wider definition of evolutionary dynamics, which includes social dynamics and cultural evolution as well, with fitness, we just mean their ability to reproduce their behavior. So it can be in a cultural way as well. If my behavior is more successful, it will reproduce with a higher frequency, right? So this is the basis for the evolutionary dynamics. Now, the thing is, all of this is interesting, but how can we actually measure if a given strategy, so let's say cooperation, is stable or not? And here I'm going to do a bit of a recap. I'm taking some of these ideas from Gosha's lecture that she did 1 year ago. And originally, the way that it was defined was basically that an evolutionarily stable strategy is one that, when adopted by a whole population, it won't be replaced by introducing individuals with other strategies onto it. So let's say we have, a group, a social group, where everyone cooperates. If we introduce a defector in there, if the defector does better, it means that the defector has a chance to replace the population. But if he does worse than the cooperators against the cooperators, which is basically what this means, the first point means. So when we say ESS larger than ETS, is basically the payoff received by the stable strategy, let's say the resident strategy, the one that makes the whole population. When those individuals receive more against themselves than the mutants, the new introduced individuals receive against the residents, we say that the resident strategy is an evolutionarily stable strategy. Otherwise, there is a weaker criterion, which is the second one, in which case, basically, this means that if the new introduced mutants do as well against the residents as the residents do against themselves, then we need to make sure that for the residents to be stable, then the residents need to do better against the mutants than the mutants do against the mutants, okay? This is it's already a bit of an abstract formulation, but essentially what this means is that when we introduce someone new onto the population with a different strategy, for the resident one, the previous one, to be stable, it needs the stable one needs to do better against itself than the new introduced mutants, okay? Now, these concepts change a bit when we go into finite populations. I'm not going to get very deep, go in depth on that, but essentially when we consider, instead of an infinite population model, which is already, they use a different set of tools, they use differential equations to study, etc. Here we are talking about stochastic models. Things are a bit different, but new effects emerge. But in the particular case that I'm going to present next, this original idea of an evolutionarily stable strategy is enough to understand what's happening here, okay? So let's look at the previous game that I talked about, the donation game. So when we look at the donation game, with in mind the things that I was just presenting about the evolutionary stability, let's imagine a population of cooperators. So what do cooperators get against cooperators? They get B minus C. Okay, and now we think, what do defectors get against cooperators? They get B. So B is actually larger than B minus C, which means that cooperators are actually not stable against evasions by defectors, right? Because if we have everyone in the population being a cooperator against the rest of the population will get B minus C. But if we introduce this new strategy defection, the defectors will do better because B is larger than B minus C, okay? So this means that cooperators are unstable against the invasion and fixation of defectors, okay? So let's look at the other possible strategy that could be stable potentially. So defection. And now when we have defectors against defectors, they will receive, as you see here, they will receive 0. And cooperators, if we introduce a new cooperator onto this population, they will receive -C, okay? Again, 0 is larger than -C. And this means that defectors are stable against the invasion fixation of cooperators. So because defectors always do better than cooperators, regardless of who they're facing, we call this a dominant strategy, which means that defection is stable and cooperation is not stable, is unstable. So now the main thing is like cooperation fails. But how can we explain this if we see, like as I was showing before in all those different cases in the beginning, we have examples from evolutionary biology, we have examples from evolutionary anthropology, we have from animal behavior, modern human societies. How do we see cooperation being a transversal trait to all of these different complex systems? But at the same time, it's a type of behavior that is not explained by evolutionary models. So for sure, we need to have other overlapping mechanisms to guarantee that cooperation evolves. And that there are a lot of mechanisms that have been proposed so far. This has been an open field for like about, let's say, 20 plus 25 years. A lot of people have used these evolutionary game theory models to study what kind of mechanisms can be at play here to guarantee that cooperation evolves. And one of the mechanisms that has been widely studied is, of course, population structure. And this is introduced onto evolutionary game theory through evolutionary graphs or evolutionary graph theory. Okay, and this is where we're finally heading to. So before we get into that, where do these come from? Like, why do we have a graph or a network science, or let's say a graph theory view of these interactions in complex systems? How is this justified? So for once, of course, this is where our main motivation is coming from, is that cooperation is not evolving under well-mixed populations. But also, when we look at real populations, they are typically not well-mixed. So if we think about like an office space, for instance, individuals that maybe are, if we have people working in this office space, they'll more typically interact with those around them. So if we are talking big office space, like 800 people, we're very likely not going to interact with every 799 of them, but probably are going to interact with more the ones that are either in our department or around our physical space. So we have basically these networks or graphs emerging out of the interactions that we have with other individuals. If you think about your classrooms, for instance, not physical ones, but if you think about your cohort, like the people that you started your degrees or your studies with, you're probably not interacting with all of them at the same frequency. You interact more often with some than with the others. And based on this, you can look at your interactions and say, okay, if I interact with someone with, let's say, person A, I have an edge. I am a dot, I am a node, and I have an edge connected to person A. And if I don't interact with person B, I don't have anything connecting to them. And basically, if we draw these edges between all the connections that exist in a group, we form this notion of a graph or a network, which can be subject, as I was saying, to physical constraints. In this case, could be the 2D floor plan of an office space. We can draw, as I was saying, the social connections between all the people that are present in that floor, but also, and as I was saying, they are subject to physical constraints, but also if we look at social networks, and we look, for instance, at virtual social networks, and we look at these platforms like Facebook or Twitter, of course, these have very specific structures, okay? They can be huge. They can have millions or billions, in some cases, of individuals or nodes. But also, they can be huge, but at the same time, they can have very small world effects. So, for instance, one experience that was made that became very famous, like already a long time ago, was an experience where basically they gave a few letters to random people in the US, and they asked them to try to get those letters to someone specific. They gave some information about the people that they wanted them to send the letters to, and they basically said, you have to send this letter to the person that you think is the closest to this person here, let's say person A. And this person A, I'm not sure if this person was a lawyer or something like this, but basically they gave a bit of information about the person. And basically what they found was that on average, the letter would be sent between 6 people. So the first person that they gave the letter to would send to someone, then this would send to someone else, then this third person would send it to someone else. And on average, they would take 6 people, so 6 degrees, to reach the final destination, to reach the person that they wanted it to reach. So basically, even if you have, let's say in the US, you have around 300 million people, but they basically, the main idea was to show that any 2 people in the US should be separated by only, on average, 6 degrees or 6 people. Basically, it means that even if you are on Facebook, if you consider not only your friends, but your friends of friends, your friends of friends of friends. So if you basically consider friends to the 6th degree, you can almost get everyone on the Facebook social network, or like a very big part of those. So basically, networks and social networks have all these different characteristics. They have a lot of particularities, but essentially, when we are considering well-mixed populations in the models that we're introducing before, we are not considering the the way that people connect in real populations. And so this is where evolutionary graph theory comes into place. So we know, how can we introduce these concepts of like network theory or graph theory onto our models? And this was done in 2005. Basically, the way that they suggested was that, well, let's consider that each individual that is interacting in this population is one node of a network. Here we have some examples of networks. These are lattices with 4 degrees, for instance, a square lattice where each dot, if you see, has 4 connections to other individuals. And basically each dot here, each node, is one individual, and the edges that you see are their neighbors, or connect them to their neighbors. And what is considered in evolutionary graph theory is that, let's say so the individuals, for one, they interact only with the individuals in their neighborhood. So let's say one of these dots can only interact with those with whom they are connected to, with those other dots with whom they have an edge connecting to. Okay, so if you look at any of these networks, it is relevant to us to, one, consider how many neighbors each individual has on average. And then we are going to see that these 3 quantities here, K, I, and J, are enough for us to calculate the fitness that each individual would get. So I is the average number of cooperators that each cooperator will have as neighbors, and J is the average number of cooperators that each defector will have as neighbors. Okay, and based on this, you can calculate that cooperators should get a fitness of I times the benefit. So because they are connected to I other cooperators, they'll get the benefit I times. Okay, and they'll pay a cost C for each of their neighbors because they're interacting K times. So they are paying the cost K times, but they are only receiving the benefit from their neighbors I times, because that's the number of cooperators they are connected to. Whereas defectors will get J times B, right? They are connected to J other cooperators, and they never pay costs. So these basically are the fitnesses of the 2 types of individuals in one of these networks, okay? And finally, it's worth mentioning that not only the structure of how individuals are connected affects their fitnesses, but also affects who can replace who, okay? So we're talking about this evolutionary process where I will basically have an offspring and someone will die and I'll replace this person with my offspring. So in this case, this is only possible. So A can only replace B if they have an edge connecting one to the other, okay? So basically structure affects their fitness and who can replace who. And based on this, if we look at these fitnesses, this is the core part now. What was shown in 2006, and I'm here citing this paper, which ended up being a very central paper on evolutionary graph theory, they basically show that when you consider networks where everyone has the same number of connections, so this is what we call a regular graph. So the one where I was showing before that everyone had 4 connections, every dot had 4 connections, it's a regular graph. And they show that cooperators have on average 1 extra cooperating neighbor than defectors. And this is so because if you think about it, as the behavior of cooperators spreads through a network, because remember, they can only pass their behavior to their neighbors, as it spreads through a network, they end up being more often connected to other cooperators than defectors do. Okay, so on average, if I'm a cooperator, I have a higher probability of being around cooperators than the defectors, right? And this basically, let's say this intuitive reason is basically summarized by this relation. So a cooperator will have on average 1 extra neighbor cooperator than a defector. And if we replace this I is equal to j plus 1, if we replace this in the previous equations for the fitness, we can basically show that cooperators have a higher fitness if B over C is larger than K, okay? So basically, B over C larger than K, it's what you can see in this black box here. B is the benefit, C is the cost, and K is the average degree, so the number of neighbors that each individual have. And what they show is that if the reward to cost ratio, so if we divide the rewards, the benefits that they receive by the costs that cooperators pay, if this fraction is larger than the number of neighbors that each person has on a network, then cooperation can evolve. And this is a very simple rule that they found. Here, I'm obviously not going into like all the calculations that they did, but it was quite a lengthy set of calculations. But basically, the main intuition behind it is that because the process has a viscosity, they call it viscosity, but like basically because cooperators pass their behavior to the next neighbor, then to the next neighbor, and the behavior spreads through the network like that, cooperators are more often around cooperators. Because of that, they can receive benefits slightly more often. And if the benefits are large enough, they can basically evolve. Yes, I think we have a raised hand. I can't see the chat, so I can't really open if you are writing questions there. But yeah, I can see a hand raised. So
Hello,
hi.
I have a question. As you said that if we have a cooperator in the graph and it is like surrounded by its neighborhoods, which are also the cooperators, so is there any specific rule that this cooperator will replace its offspring by their neighborhood? Like, I mean, it will follow the N4 neighborhood rule or N8 neighborhood rule, or what it will follow to replace. For example, if we have a cooperator in the graph and it has 4 neighborhood and all the 4 neighborhood have the same relative, let's say, fitness or probability to be replaced. So which one it will replace? Like it follow any specific rule? Like we have the idea of N4 neighborhoods and N8 neighborhoods, so can you please explain that?
Okay, maybe I'm not sure if this is what you're asking, but I try to maybe. So, for instance, take this example of I have two networks here, right? So, in the one on the right, the evolutionary process goes as it follows. So, basically, you choose one random person, one random dot from the population to basically be removed, to die. And this one is the one that is now in gray, is a question mark. Because then you ask, who is going to replace these? So you look at all their neighbors, and you have a cooperator on one side and you have a defector on the other. And here we only take into consideration the closest neighbors, so the ones they are directly connected to. I'm not sure if that's what you're asking. And then what we do is we consider that from these two, we consider that they are going to replace the one in the middle, the one we chose for death, proportionally to their fitness. So let's say if the cooperator on the left of this gray dot has a higher fitness, it will have than the defector on the right. It will have a higher probability of replacing the one in the middle than the defector on the right. Okay, I can't really use my mouse, so I can't really like show you on the network, but that's the main idea. So that's how the evolutionary process goes, and you consider only the ones that are directly connected to the first. So you choose one individual for death first, and then you choose their direct neighbors. Okay. Was that exactly what we were asking, or was it something slightly different?
It was slightly different, but it's okay. We can discuss it at the end of the lecture.
Okay. I mean, yeah, I don't know. Yeah, I'm curious now. But yeah, maybe we can do it at the end then. I'll let Fajid decide or like moderate. Okay. So yeah, this is the main result that they got. This is the main result that they got. Basically, cooperation evolves if the benefits over the costs are high enough. And high enough, basically the threshold is the average degree, this K here. And if that happens, we see cooperation succeeds, contrary to what happened before on the well-mixed populations, right? However, this doesn't tell the whole story. So by taking on evolutionary graph theory and using it not only to study regular graphs, but to study scale-free graphs, some other things were concluded. So first of all, I'll just like say that with the way that this was considered in this paper that I cite here, it's also a very important paper in the context of evolutionary graph theory, is basically that instead of looking at just a network where everyone has the same number of connections, the same connectivity or the same degree, basically the same number of neighbors, they considered a network obtained through the Barabashi-Albert model. And in this model, basically you consider you consider two things, or it's characterized by two main aspects. One is preferential attachment, and two, its growth. Basically, to build the network, what they did was they start with one or two dots, one of two nodes, and they say now we are going to make the network grow. So this is growth. And they add one new node, and they say this node will connect to any of these two, but like proportional to their degree. So basically, if they already have a lot of connections, they will have a much higher probability of this new node being connected to them instead of the other, right? So what happens here is that because you're building the network like dynamically, you start with two nodes and you add a third, and then a fourth and a fifth. When you're adding the 100th node, very likely you'll have a small set of nodes that have a lot of connections and a large set of nodes that just have one or two connections. So basically the way that the network will grow is into like these weird shapes where you have clusters or hubs. You have nodes that will have, let's say, like if you have a network with like 1,000 nodes, you have some nodes will have, let's say, 500 or maybe 100 or like hundreds of connections, and some other nodes will just have one or two. So you have the ones in the center, in the hubs, in the clusters, and then you have some on the periphery of the social network, okay? And what was done in this paper is basically using these networks, not considering, so you first build your network, and then with the fixed network, so it's not dynamic anymore, you say, now everyone plays games. What happens? Do we see cooperation evolving or not? And that this outcome basically can reproduce. So like these games on these scale-free networks is a way of modeling a lot of different social and biological real systems, because the truth is these scale-free networks are found across a lot of the research fields that we were talking about before. If we talk about not only biological, social systems, if you talk about the World Wide Web, all of these things, all of these different systems have, or not all of the systems that we encounter in this context, but like a lot of these systems have these scale-free characteristics to them. And if we allow individuals to play games on these complex networks, what they observed, now we have here a lot of information, but I'll just try to give you an intuitive idea around it, is basically that if we consider the same average degrees, so that on average, everyone has the same neighbors, but because this is a scale-free network, some will have a lot of neighbors and others will just have maybe one. So in these particular networks, what they observed was that, scale-free networks hold cooperation levels much higher than the corresponding regular networks. So this is even going beyond what I was showing before. So regular networks or regular graphs were enough to see cooperation evolving already, because they allowed, as I was saying, for cooperators to be closer to cooperators through the evolutionary process. But not only that, but if we consider more complex structures, like the real ones that we see in biological systems, in social systems, they show that this boosted even more the levels of cooperation that were observed in real systems. So this is going an extra mile, right? This is going even beyond the baseline of regular graphs that already promoted some sort of like cooperation, the evolution of cooperation, right? And you can basically see these here in these plots, because the red lines are basically almost at the 100% for frequency of cooperators for any value of parameter B. And this B, I'm sorry, I should have changed this, but this B from this paper is a bit different from the B, the benefit that I was showing before. But the main idea in this plot is that if they explored a lot of parameters and they saw that for a very large part of these parameter values, cooperation evolved for scale-free networks, but not for regular networks. So maybe even when the previous rule that I showed, the B over C larger than K, does not apply, in the case of scale-free networks, that we still might see the evolution of cooperation. Okay. And this is very, in the end, it ends up being very powerful and shows that in fact, population structure might be one of the most likely, or one very likely mechanism to explain why we see cooperation evolving in a lot of these biological and social systems. Okay. I didn't talk about the other mechanisms. It's not on the scope of this lecture, but there are other mechanisms like direct reciprocity or indirect reciprocity. We can talk about punishments, or basically these reputation systems. There are a lot of other ways in which, or through which, we can guarantee that, or we can explain that cooperation evolves in these systems. But one of them is clearly population structure and this graph structure or network structure that real populations follow. Okay. Now, I'd like to, maybe just to finish this talk, I'd like to mention very briefly that there are other extensions of these sort of models. So these were already the ones that the results that I was showing before, they are already from a few years ago, but since then a lot of things have been done. So for instance, these sort of complex networks have been studied not only in fixed networks, but also allowing for individuals to choose their own connections. So sometimes they extend these models to allow them to rewire. So let's say I don't like this link. If I'm a cooperator, I don't like to be, and I'm surrounded by defectors. Not only can I change my behavior to defect because I'm not benefiting from anyone cooperating, but I can also say, you know what, I'm going to remove all these friendships that are toxic to me, and I'm going to form new friendships and new connections. So sometimes we do that in real life as well. We delete some of the edges in our social networks, even if not consciously. Sometimes we end up doing it. And we form other connections with people that might be more, let's say, helpful, or might be more cooperating in the context that are relevant to us. So there are all these sort of like strategic rewiring on networks that also can add other layers to and other levels of cooperation boosting. We also, and in another one of these extensions could be considering movement models, through which we can have strategic movements through networks. And so we're not embedded in a static or a fixed social network, but in fact, we move through life and through our social situations, our social environments, and we end up meeting a lot of people on the way, right? And what this framework that was introduced into 2012, and it has had a lot of developments lately. Basically, what this framework introduces is basically that we don't only have social networks, but social networks are something that can emerge from us moving through spatial networks. So basically, if we consider a spatial network, which is defined here by these squares, we each have our homes, let's say, and we move through these networks. And as we move, we end up meeting different people. What they consider is that when we're present in the same square, so in the same node of the spatial network, with, let's say, a group of other people, they will interact. They will play a social dilemma, which here can be a group dilemma. It can be more than two people. And this might be a good, like the public good dilemma might have a good outcome, and we might all cooperate and produce something together. And as individuals go through the network, they basically play these games, they receive their payoffs, and they basically accumulate those payoffs. And then evolution is considered based on basically the individuals that you meet in this network. So there is an underlying interaction graph and an underlying social network. But the social network itself is not defined from the start. It's something that emerges, let's say, from us moving in a network. And what I was showing here is that if individuals only move locally, so around their surrounding, in a short range around their surrounding, and if they move independently from each other, the evolution of cooperation is very similar, or the mechanisms are very similar to the ones that I was talking about before in fixed social networks. Okay. However, if their movement is conditional on who they meet, so let's say if I'm meeting with a group of defectors and I don't like it, therefore I'm not satisfied with it, maybe I'll say, okay, I'm going to move. But if I'm in a good group of other cooperators, I'll say I'll stay, and I want to maintain these sort of interactions. And if we consider this, what basically they showed was that this leads to new dynamics. So it's not only the viscosity of the process that I was talking about before that guarantees that cooperators are present more with cooperators or have more cooperating friends than defectors, but also because they can move and they can aggregate. They kind of have this assortative behavior. They kind of cooperators stick to cooperators and they run away from defectors. And this can lead to even higher levels of cooperation. Okay. So these are basically extensions of the original graph or evolutionary graph theory models. There are a lot of different types of models here. And yeah, a lot of things have been studied, but basically the main idea that I wanted to pass today to you was that graph theory comes from basically the fact that cooperation cannot be explained in well-mixed populations very easily. And two, the fact that real populations are structured and they have these complex network structures. So when we actually apply these complex networks to the dilemmas, we see that cooperation has a much higher chance of evolving. Okay. So thanks a lot for listening. I have here if you'd like a bit of my information, you can find some more information on my website. You can scan this code if you want. These are my collaborators and supervisors who have been working on some of these projects together. And also, of course, our funders. Of course, I always have to thank them. Vajid knows it. And of course, to you for being here on a Saturday. And I hope it was an interesting talk to you. And of course, if you have any questions about the talk specifically, but also about what it means to do a PhD in general, like how does the process goes of applying to PhDs, how actually doing one, and being a few years into it, I think is, feel free to ask me any of these questions. Yeah, and thanks again.
Thank you so